Okay, well, might as well start. Okay, so today's our last lecture, and we have a guest today. Steve Lyons is the person who teaches the course on intellectual property, which is also part of Tom Inger's structural materials course. So I think you're teaching next semester, aren't you? Hope so. Hope so. Yeah. Okay. Okay, so let's see here. First, we're going to talk about a couple of things here, and then we're going to talk about bicycles and cars and share screen. Okay. There we go. Okay, so most of our lecture last week was about bicycles. Last week was the bicycle lecture. And we talked about the history of bicycle frame technology. And we didn't just talk about this because I like bike riding. We talked about this because I think it's a really good example that shows how the principles we've been talking about in this course can be used to design lightweight structures. The idea of engineering materials for maximum strength to density or maximum stiffness to density, and then engineering the geometry of a structure so that it can best handle the load in terms of stiffness or strain energy or strength, fatigue resistance. And bicycles have done this, I think, tremendously well compared to probably pretty much any other consumer product. I always say that the bicycle frame is one of the most highly engineered products, consumer products from a structural optimization perspective. And I can guarantee you your car, no matter if it's a McLaren or a Toyota, is nowhere near as well engineered as these bicycles. And the reason for that is that people go crazy about spending money on these things if they're passionate about it. So the money's there in the overall product for people or for the engineering companies to figure out how to do the best job they can to make these things lightweight and efficient. So to go through this quickly, we start off in the 70s here with Colnago. And this is a chromoly steel tubing that's brazed together in steel investment cast lugs. We talked about heat-treated chromoly and silver brazing. We talked about really high-strength steels, a margin steel that's stainless with like a yield strength there in sort of 1.2 gigapascal range. We talked about the next generation of steel bicycles that are no longer tubes, but rather halves that are welded together. And we talked about aluminum. The first aluminum bikes were pretty ineffective, I would say. They weren't very stiff, they weren't very light, they weren't very fatigue resistant, but at least someone got something out there. And Gary Klein from MIT changed all that. Gary Klein developed this company and this technology during I guess it's the January period between semesters. Turned this into a real company that eventually got bought by Trek. We talked about the first titanium frame from Teledyne. This frame was made out of commercially pure titanium, and it was horrible to ride, and it failed all the time. It was incredibly expensive, but it was the first one out there. This was dramatically improved, mainly by Lightspeed and Merlin for the years, maybe in the mid 90s, where they started using alloy titanium, 3.2 and 6.4 titanium, and they were able to produce bikes that were significantly lighter than the steel bikes before them, and more fatigue resistant, but they didn't ride real well because the material wasn't that stiff. And we talked about carbon fiber. The first carbon fiber bike was in the mid 70s, and this was really just carbon fiber that was wrapped around wrapped around an aluminum mandrel, and then it was glued into steel lugs. This frame again wasn't real successful in the marketplace because it wasn't that stiff, it wasn't that light, it wasn't that fatigue resistant, it wasn't that safe to ride. So it really wasn't successful. Kestrel changed all this. Kestrel changed all this in the mid 90s when they made the first monocoque frame. They called it a monocoque. I would argue maybe it wasn't a monocoque, but the point being is that they molded this carbon fiber bike out of one piece, or many pieces of carbon fiber, but it became one piece after it was cured. The first carbon fiber bike to win the Tour de France was the Look KG86. This bike used carbon fiber tubes that were bonded into cast aluminum lugs. The frames were somewhat lighter, not very stiff, more fatigue resistant, but they worked. They weren't the greatest, but a lot of people won races on them, including this guy here. And then the most modern bicycle frame that I can come up with right now is probably this this tread frame here, which is made out of high modulus carbon fiber. Okay, and it's all tuned in a wind tunnel for wind resistance, and not only in one direction, but they also tested different oblique directions to see how much drag these bikes create when they're not going straight into the wind. And most of the time you're out there riding, you're rarely going directly into the wind. You're always going at some oblique angle. So the drag at those oblique angles is important. I mentioned high modulus carbon fiber. So I don't know how much you guys know about carbon fiber technology, but there's carbon fiber and then there's real carbon fiber. The longer they pyrolyze the material, they turn the organics into how should I say this? They start off with a bunch of different molecules on there. They burn off everything that isn't carbon when they make carbon fiber, and then they cook these things under tension to get the molecules as aligned as possible. The longer you cook it with this tensile stress on the fibers, the stiffer it becomes, but it takes more energy, more money, so it costs a lot more. When you're building a bicycle that costs $13,000-$14,000, you can afford to use a kilogram or 2 kilograms of the really high modulus stuff. Okay, so that was bicycles. We should probably talk about these bicycles right here since they're here. So you guys can come and take a look if you want. This is from 1981. This is a bike called the Navy Mercs. It's made in Belgium, and this is typical of what a pro would have written in the early 80s. Most pros wrote a bike exactly like this. So this is the tubing is made out of chrome moly. It's not heat treated. The thickness of the tube is about right here in the middle of the top. It's probably about 600 microns. So not the thinnest, but still pretty thin. So and then the lugs, you can see where the tubes go into these lugs here. These lugs are made through a process called investment casting or lost wax casting. And then the tubes, some craftsman comes in here, he inserts the tube, and he gets it with a really fine acetylene torch. Okay, and he heats up the area around it just ever so slightly, just the minimal he can. He puts some flux on there so that there's no oxygen around, it doesn't corrode. And he gets into the little piece of brass. She gets into a little piece of brass, and this touches the lug, and it liquefies in an instant. And then capillary action sucks the brass into the joint so that it's well bonded to do it right. I've tried to do this a couple times. It's really difficult. It's really difficult. So anyway, so this bike is from 1981. Steel frame, basically every part's aluminum. What else?
What size frame?
This is a 55 centimeter from center to center. Okay, and like I said, it's all pretty much aluminum. There's very little steel here outside the frame. And this is 81. So Steve, your bike is from what year?
Oh, let's see. I think that bike now is about 10 years old.
You became the shoes.
It comes with nothing, trust me. This, by the way, is one thing Don and I think maybe you can tell the passion that we share is bicycles. And I can tell you right now, this is a classic. Not just from a bicycle standpoint, but from an engineering standpoint. If you come up and take a look at the welds on this bicycle and compare them to welds on any other bicycle you see on the road, you will see a big difference. This is art as much as it is material science and engineering. If you look at these welds, they're just absolutely pristine, they're beautiful. And they're a representation of the engineering and the manufacturing material that goes into this bicycle. Like I said, I wish I owned one of these. And I own a lot of bicycles.
How many do you have?
Assembled or disassembled? Assembled, I think,
That's not too bad.
disassembled, I have probably 15 or maybe as many as 20. Because when it comes to bicycles and bicycle riding, not every bicycle is suited for every race. I have bicycles, and I'm sure Don has bicycles that go uphill better than other bicycles. I have bicycles like this one that are built to go in a straight line faster than anything on the planet that is powered by human beings. I have bicycles that are built for long distance races, 200K, something like that. I have bicycles that are built to go a short distance. I have bicycles that are built for a course with lots of curves in it or hills, and each one represents a compromise, if you will, on the ideal. This bicycle, which is made by a little fellow in Zurich by the name of Andy Walzer, is the most expensive, lightest, fastest human-powered machine in the world. You can pick one up for the base sticker price of 46,599 euros.
Ouch.
But this one actually has several options, so it's quite a bit more expensive than that. Andy has a little shop in his basement in Zurich. And if you want to buy one of his bicycles, you have to go to Zurich and you have to be tested. The first thing this bicycle is made for is ergonomically for me. It's built to fit my hip to knee length and angle. It's built for my torso. It's built for the length of my humerus. And as you can see, it has a very aggressive geometry. If you compare it with the Eddie Merckx, look at the position of my butt and my head.
Is that a time trial?
This is essentially a time trial bike. That's right. Like I said, it's built for one particular purpose. You can also use it in shorter criterion races. But the longest you can probably survive on this bike is about 100K if you're at peak fitness.
For your back circuit too much.
We say this bike comes with its own lifestyle, because when I first purchased this bike, as you can see, the very aggressive position, it is built to recruit as many muscles as possible. On this bicycle, which is a road bicycle as opposed to a time trial bicycle, you're recruiting muscles about in this area. This bicycle recruits muscles from here to the middle of your back. You literally have to train in order to ride this bicycle. But on this bicycle, I'm better than people who are probably 20, 25 years younger than me. The advantage that I have with this bicycle is I beat pro riders on this bicycle.
And then it's essentially just a money game. Who can I mean, you have to be fit, obviously.
It shares out car racing, yes.
Yeah.
It's not a money game, because if you put yourself on this bicycle, no matter how much money you spend, if you are not trained to make this thing go, all the money in the world doesn't mean anything. All the money in the world gets you in the race. This guy has made all of the bicycles until recently, when the UCI changed the rules. Every bicycle that you saw on the Tour de France winner, whether it said Trek or Giant or whatever, was built by this man.
For the time trial. So you mean for the
time trial.
Yeah, because doesn't UCI have weight limits? My guess is this is well under that, yeah?
Well,
20 kilograms.
there are all kinds of ways to get this bike to weigh as much as it needed to weigh. Okay, one of the things is that you can actually add weight to the frame in order to bring it within the rules. This bike is 100% UCI legal, 100%. But you can't run it in a race now, because what they used to do is they used to paint Trek on here or Giant on here or Look on here. And now, because all the money comes from sponsors, the UCI requires you to use an off-the-shelf bike. So this is an off-the-shelf bike.
Even for time trials?
Even for time trials. They don't allow you to use them anymore. Anyhow, the things that are interesting about this bike, you might want to take a closer look at it, is the way the carbon fiber is laid down. If you can look at it, because I don't have it in in some of the places it's not painted, most of the places it's not painted. So you can look at how beautifully the carbon fiber is laid down. You go over there and you do a time trial for Andy. He puts you on an ergonometer and he measures the amount of wattage that you can produce. Cipollini
These are pro riders.
the pro riders, Cipollini is famous. they can produce upwards of 2,000 watts. I'm on my best day a 1,200 watt person. So
500 watts.
so the bottom bracket on this bicycle, if you can turn it around so we can see the bottom bracket on this bicycle, which is where all the power transfer takes place, is made for me, not for Triple E, okay? And that saves weight. But it's also laid down differently for me than it would be for Triple E.
This is the bottom bracket area where the crank spins and right.
And one of the cool things from an engineering standpoint is he could have gone with the latest carbon fiber cranks, but he has milled aluminum. He does it himself in his lab, forges it, and he mills it out with a hand tool. It's lighter and stiffer than the best carbon fiber in the world. I asked him, why don't you use carbon fiber cranks, Andy? He says, because the aluminum cranks I can make are lighter and stiffer than, and what you want with cranks is great stiffness, because you don't want to lose any power when you're spinning it.
You can see how it's milled out on the backside and how he's increased that bead, you know, the bead on the one moment inertia that I showed you guys. How he's increased that by milling it out and making it wider. It's still keeping the weight down.
And Andy didn't have the benefit of John Baskin's structural materials class or going to school at MIT and learning from Tom Eager. Andy learned this by trial and error over 60 years of making bicycles. He really is this mad scientist. And when you go to his house, it's like stepping into this Xanadu for bicycles, okay? But he learned all this himself. And all the big manufacturers try to copy him. And so when you buy a bicycle from Andy, you have to sign an agreement which says that if you want to buy his bicycle, if you want to sell it, you have to sell it back to him. Because what they were doing, what Giant did, which is the big company in Taiwan that makes wonderful bicycles. One of the reasons they make wonderful bicycles is they got a hold of one of these bicycles and they took a hacksaw to it and they cut it into 1-inch pieces so that they could study how the carbon is laid down. You know, the way it's done in a custom bicycle, it's done completely different than it is in a factory where you're making bicycles for everybody, from Steve Lyons and Don Baskin to Mario Cipollini. It's kind of like, you know, it's the difference between a custom set of clothing and clothing that you buy off the rack. But if you look at this bicycle, the way it's engineered, it's totally functional evolutionary design. It's made to be stiff where a bicycle needs to be stiff. It's made to be flexible where a bicycle needs to be flexible. It's made to be aerodynamic in ways that it needs to be aerodynamic. Everything you can look at this, you see in this bicycle is the optimal design for something going from here to there in a straight line faster. And it's what everybody is copying right now. This bicycle still can't be beat by anything that's made by mass manufacturers, and it's 10 years old. The technology you see on this bike still hasn't come into the Tour de France. It will, but it doesn't. And it has a lot of stuff that you know is kind of not so cool anymore. It has mechanical brakes instead. It doesn't have hydraulics. It doesn't have disc brakes. One thing that you may not notice unless you really know about bicycles is that it has one of the reasons this is so expensive is because it has the drops are custom. They're not as wide as most bicycles are. So all the wheels on these bicycles have to be made with they have to be custom made. They're made with custom bearings. These are all ceramic bearings on this wheel. One wheel on this bicycle is $18,000.
But what Steve's talking about is they're going narrower for better air resistance.
Right.
You know, their drag is the
Drops are like this.
Right.
These are about 6 millimeters smaller, and the
reduces
savings.
the frontal area, so it takes the drag down.
But actually, the funny part is the front wheel is standard. You know, that's right off the shelf. And another funny thing is this fork. We substituted this fork for Andy's fork because this fork has a little bit of rake in it, and that creates a little bit more stability. The forks on Andy's bike again, are built for one thing, going fast and handling, and unless he doesn't care about the rider. His attitude is learn to ride it, get more fit. This is the way it should be designed from an engineering standpoint. But we substituted this fork because it got a little bit more weight, and that gives the bike a little bit more stability. Forks, right, the forks that Andy's bike come back here about about 10 millimeters, almost half a centimeter. So they're very unstable, very twitchy. If you just turn your head like that, the bike turns to the left. If you turn your head like that, the bike goes to the right. And at 40 miles an hour, that can be concerning. So
It's also bad for riding long distances because it's exhausting to keep straightening the bike out.
This bike is really exhausting. I rode it in an Ironman once, and honest to God, I could barely walk when I came on it. I did 112-mile bike in 5 hours and 10 minutes, but my run was nothing because I completely exhausted myself physically. So when you're in races, the bike you use really depends upon the type of race that you're in. So it's worthless in an Ironman race. But in a 40-mile time trial race, no, I defy anybody.
There's very little metal on this bike if you think about it. Like that bike is all metal. There's like some leather, tires are rubber, but there's very little. There's basically nothing that isn't metal on that bike. This bike, there's very little metal, and even now, there's bikes that have even less metal than this. Pretty, they get to the point where the only thing that's metal are the chain and the gears, basically.
And they actually have carbon fiber chains now, but
They do.
Yeah, but they're not that reliable. And again, these are caliper brakes. They're made of aluminum. Again, Andy chose them not because they're cool, but because they're fast and they're functional. And this thing is not made to stop. So, when you're going 40 miles an hour, it's like trying to stop a train. Why? Because it's not built to stop. So he doesn't put brakes on it that will stop. All he cares about is you going in a fast line, straight line faster than anybody else. But I encourage you to come up and look closely at the way the carbon fiber is laid down. Again, like the brazen welds in this bike, it's as much art as it is science. And that's why everybody copies his bikes.
So just keep in mind, there's 30 years of development between that bike and this bike. Just like that. And
Any questions on the bicycle?
Yeah.
It's 10 years old.
Yeah.
Still not, this technology is still not really used in the Tour de France part of that.
No, because they can't afford it.
you feel the.
So that's like $100K.
The Tour de France is a way to make them sell, basically like
Yeah.
advertise,
trying to-
make good.
They're trying to.
advertise. Yeah.
Right, in the old days,
They put it right close to the tire.
money was no object. Now they make them ride off the shelf.
These things are very focused.
Although
Drag down.
So bespoke in some.
there are openings in the rules, and where they do, they run
I'd
in,
be
like,
afraid to crash.
like for chains.
I would too.
Some of the sort of.
Look at the airport section on the bars, tiny little brake handles.
Is the,
I don't know, it would be
the
more
carbon
expensive
fiber
than
one.
medical
Is
bill.
the
or the
chain
bill to
like,
fix
why don't you go to something lighter like that?
I think that's a country.
Probably. It's so pretty.
Yeah, we'll push together. Carbon wheels.
How do they like wrap carbon around a mold? How do they get the carbon in the perfect shape?
So there's a lot of ways to do it, but I think probably the way they do it
This
is
is
they
the
have
rule
a female mold,
Mhm.
and then they have like a silicone mandrel.
Is this a good
They
nickname
wrap it
or a
around
bad
the silicone
nickname?
It's a name I've
Some
heard.
Some goes in the,
Oh,
goes
no,
on next.
I broke it, yeah. on this
Yeah.
one,
But the thing
too.
is, think about silicone,
Broken
you
almost
have it
every
expands.
time.
So they take the whole, what's all the carbon fiber pieces are laid up and it's in the mold. They take
Yeah.
the whole thing,
Actually, I did a
turn
physics.
it, furnace on, and as it gets hot, the silicone expands
Right,
and it pushes the
Road
carbon fiber against the mold.
cool.
Okay,
Somebody
so that
trying to,
you get maximum compaction.
Yeah,
get a
yeah.
parking
Minimum porosity.
That's so
Cambridge
cool.
Street,
It's pretty
and
clever.
Starbucks hit me in the rear.
The tires are actually, they're glued on These are
fractured
tubulars, right?
my.
What? What do you do if you have to change a
This is
tire?
my shoulder. I brought the
I got a problem. These are actually glued onto the rim.
Are you
It's
serious?
It's a special kind of tire called a tubular. Tubular is actually rounding
I had a
cross
professor
section.
early on here,
And then glue it to the, glue it to the rim.
said, it's not a question of.
Whoa.
Yeah.
I get way too many thoughts for that.
Well, I got a lot of flex. You don't
There's
use
two
it
kinds
for
of
training,
things.
you use it for
Those
racing.
who
on.
have.
Right, and then you hope you don't get
You
a
don't
flat
get
during
a flat
your
tire,
race.
right? If you're really, it's a
Yeah.
really big kind of getting bike.
Yeah,
Instead of a
wow.
new tire.
What?
But it's still a lot of fun.
Yeah, so the tires on that bike are called clinchers and they're U-shaped,
Uh-huh.
okay? And then little hooks, like little beads around the.
So things that are going
circumference
away
of the
from
tire
the
that-
metal,
that help you do a
I'm
little
assuming.
bead, a little
We
protrusion.
talked about the.
Protrusion on the inside of the rim.
Yeah.
And that's, and then there's a tubing there.
Everything is
And that's what
just.
stops it from
Yeah,
ripping
that's
off.
cool.
Everything has to be a lot stronger. The rim has to be stronger.
Yeah.
Tire casing has to be stronger. It weighs more. It weighs less, but it's spinning.
Okay. Wow.
It's spinning.
Gotcha.
But yeah, these are, two glue-on sew-ups.
Mhm.
The tires are made of silk. They're about $250 a piece.
Okay.
They're inflated to 150 pounds per square inch.
You put 150 PSI in these things?
Yeah.
150?
You can actually go higher.
Really?
And the idea is to get, again, depending upon the race conditions,
Right
of
on
course,
razor, yeah.
you want to have smaller contact patches.
Is that why it says psycho here?
That's my team, actually. I knew I was gonna get a question about that, but, yeah, that's,
See them out there?
that's my team.
Usually, steel frames, these are brazed on there, aluminum frames, and they're glued on. This is actually formed in carbon fiber. I've never seen that before. That's hard to do.
When you have like
The-
a clear seam, is that a weak point?
So the change in direction.
No, it's just a PC laid out.
Yeah, that's how it's laid out. In fact, that's a really great question. Because what it does, is it's basically a demarcation point between the part of the bike that needs to be very stiff and the beginning of the bike where it needs to flex. So when you go around a corner, you want the bike to be very stable and stiff down here, but to be responsive and to go around corners efficiently, you want more flexibility as you go up to where the weight is being carried.
You want a lot of movement here, but you want it stiff down here. Okay, the highest stress area is actually right here. Right here is the highest stress part of the whole bike, right there joint. right
Yeah, that's
here.
the most unorganic shape on
It's,
that bike.
so there's a stress riser there.
Yeah.
And it's under bending, right? And this is
Yeah.
where the bending goes the highest is right here.
And you can feel, and when you're a rider, you can feel it. So you're doing 30 miles an hour, and going around a corner and you're under power because you can absolutely feel the bike flex in the places where the power is being transferred and where the weight is being borne. You can actually feel, because on this bike, you almost become part of the bike. And so when you're actually moving on the bike, you're sort of moving as one. And you're very much aware of where the bike is bending and flexing and being stressed.
Certain bikes that are good in a straight line and a sprint aren't necessarily good at high speed descents. You need a lot of cornering.
This
Oh,
bike is
terrifying.
actually, one of the wonderful things about this bike is in a high speed descent, one of the things that is really scary. You're doing 100K down a
Oh.
hill and you have trees on either side of it. Then you come to a point where there are no trees and there's a crosswind.
Oh,
I've been blown
Wow.
literally into the next lane with a bus coming this way.
ouch.
Makes
There's
sense.
nothing, absolutely nothing you can do about it.
You can anticipate it, right? You have to know that's coming out.
So, well, yeah, you have to be smart. But the very small top tube on this bike, and the fact that it doesn't have a disc on it at the present time, one of the things about this bike, the way it's configured now, is it's really good in the crosswind. So a lot of bikes you'll see, like that Trek he was showing, have a large top tube on it. On a crosswind, it's just like a sail. But but on a road bike, it's not that big a deal. So they do it. Again, everything is a compromise with a bike. The first question is, what are you going to use it for? And that's how they design it. Anyhow, that's my show and tell.
Just think about, especially when you think about, like I said, there's 30 years difference between these two bikes.
I want to see it in another 30 years.
Yeah, where do they get to, right?
Yeah.
But just think about like all the things you talked about, but designing materials for high strength and high stiffness to density, about using geometry to lower the stress in a component, or given structural member, okay? I want you to think about that, what I just said, the difference between these two bikes under that context of how are these things, how have they evolved over this 30 years in order to be lighter, stiffer, more lightweight? Think about that.
And how much your engineering is both science and art. If you look at these two bikes, it's just not science. There's an awful lot of art that goes into
Craftsmanship, you know?
craftsmanship, is another word for it. You know, it's not just one thing to know the principles, but to put them in practice and to do it in a way that maximizes those principles is the art part. That's where Andy Walzer or the people that make Eddie Merckx's bikes, so that's how you really get on a fantastic bike. It's not all equations. It's a lot of craftsmanship.
Some of that craftsmanship goes into reducing stress concentration. So they may not see it in that perspective, they may not realize it, but they're actually helping the lightweighting process by making things that are nicely made.
No, absolutely, absolutely. There's craftsmanship in the way, the direction that the carbon fiber is laid down in the bottom bracket to give it stiffness and lightweight. So that, this craftsmanship is not just for the sake of craftsmanship. It has a real functional effect on the machine.
So is the carbon fiber anisotropic then?
Yes.
They use, so on the top layer, they have the weave here because it looks nice and it's good for
Yeah.
thermal protection. Underneath the weave is UV, unidirectional material.
Okay,
And the unidirectional material, they lay up according to the stress and the loading cases.
cool.
Well, that's that's why they buy Andy's bikes and cut them apart. What they want to look at is what you can't see under here
How
is
they
the
weigh
way,
those fibers up.
he lays it down.
Was it completely trial and error, or did he do like mechanical testing or modeling?
Trial and error. No CAD, none of this stuff. It literally is a basement about this size, with bicycles all over the place, parts, almost like Frankenstein's laboratory, because you see the failures over here, like these handlebars, okay? These handlebars are his latest handlebars. They're ergonomically better than the old ones that he had. Actually, they're so beautifully built that I took the foam off of them because it feels more comfortable on my skin to be directly in contact with the carbon fiber.
Wow.
The carbon fiber is actually softer than a pillow because of the way, again, because it's constantly flexing.
Yeah, it's
What I mean-
compliant, yeah.
That's right.
Yeah.
And so when he did these bars, if you go to his shop, you'll look at the iterations that he tried. And what he did is he builds them, sends them to somebody like me or somebody much better than me to try them out. And if it's thumbs up, he keeps them. If not, he tries them again. But it's all trial and error. And he has dozens of bars until he finally came up with the right one. And that's the same for every piece.
So that's bespoke to like your shoulder width and like how close you can get your elbows together.
Yeah.
Okay.
Yeah.
That's where the money comes. They have to make separate tooling
Right, yeah,
for
absolutely.
each person, right?
Yeah, you gotta carve your molds.
I mean, that's another reason why you like wouldn't sell it to anyone except for him.
Right, because it won't happen to anybody else, right?
Like you might as well take the molds home with them.
Well, somebody with the same hip to knee ratio as me, somebody roughly the same size as me, would be great on this podcast. But maybe not as comfortable as I am.
And the guts.
To ride a bike that's
I
that
would
expensive, right?
argue that as well.
So,
It's something that I thought, like a supercar, you only take it on a Sunday kind of thing. And only if the weather's nice.
Yeah, I was gonna say with that spin of a wheel, my guess is you're sacrificing a bit of craftsman, so if you just not race it, if it's like already there.
Race it in any weather. I actually carried it over here from downtown Boston because they won't let you take it on the T in the morning.
Mhm.
And I won't let it, I'm not gonna let that on the streets.
especially with all the salt and the carbon fiber and
I
the,
put all the junk on the street now, so, yeah, it's the only bike that gets carried.
so now thinking about these two bicycles and the time between them and how they're constructed. I want to show you how that's translated into racing cars and maybe some passenger cars as well. This is a Porsche 917 It was developed in the late 60s, Porsche. And it is a space frame. It's the classic space frame. This is probably the pinnacle of the race car space frame. And these are actually, these are actually made up of aluminum tubes that are TIG welded together, right? But you can kind of see like space frame, see the kind of connection there? How they're similar in terms of the shape and morphology of the structure and the metallicness of it, and the joining methods. These frames were, like I said, they were made out of aluminum tubing. The legend has it that the tubes were pressurized with nitrogen. And they did that because they had so many failures during testing. They knew they were so close to the fatigue limit that during a race, they didn't know if they would have a problem or not with the frames failing. So, sorry. They didn't know if they would have the frames fail or not. So they pressurized these things with nitrogen. This is legend. I don't know if this is real or not. This is just legend. That they would pressurize these things with nitrogen, and then they would check the pressure in the tubes during the race to see if there was a crack that formed. Because if there was a crack that formed, then the nitrogen would have escaped. So I don't know if this is true or not. They also
Do that on helicopters, actually.
do they really?
Yeah, so the main rotor spars for the main rotor blades.
Yeah.
They pressurize them with like 10 psi nitrogen. And it's very tricky to get sensors up there. So it has like a delta P indicator and it pops a little radioactive that sticks out a little bit. That's usually shielded.
Okay.
And then there's a sensor that can pick up that radiation. And then it tells you that you have potentially, overstressed blade.
Very interesting. I want to picture this.
Oh, I don't know.
See if I can find one. Okay, so there's also a legend that they made these space frames out of aluminum, or out of magnesium tubes as well. So some of the later 911 or 917s, I guess they actually made these out of magnesium tubes. And magnesium is even less fatigue resistant than aluminum, and certainly a lot less corrosion resistant as well. So these things were death traps. Lots of people got killed in these cars. Your feet were in front of the front axle line. So if you hit something, you'd lose your feet basically. It sure this car ended a lot of careers of racing car drivers, people who had messed up feet. Death trap, absolute death trap. Caught on fire, space frame came apart. I recently built a plastic model of this. So I have a book at home where it's called the 917 archive book, and they have many of the engineering drawings from the space frame in there, among other things. So I actually bought a bunch of little plastic tubes and built one of these things, seeing what I could learn from doing it. So just plastic little styrene tubes and then glue them together with crazy glue. And I know it looks pretty simple, or maybe just looks like a bunch of tubes coming together. But what I learned that was interesting is that there's like very few right angles on here. Everything forms a triangle. Not everything, but pretty much everything forms a triangle. For example, like these tubes that go back to the engine over here, they're not actually parallel to the center line of the car. They actually come in at an angle. And then the ones on the bottom come in at an angle as well, but they're the opposite direction. So they built in all these triangles in here, because triangles are more stable than squares, because squares can parallelogram or matchbox, right? So it's really interesting to me. I learned so much from making this stupid little model that I don't know, you guys might want to do it too. It's fun to do. So I want to compare that to so here's another space frame car. This is a 1961 Birdcage Maserati. I've shown you this before. This again is a space frame made out of many little tubes. Now think of some of this in terms of the context of this car here. Actually, let's do this car. This is a late 50s Lotus Elite. This is the closest any car has come to being a true monocoque structure, because the body structure on this vehicle is made from like 3 gigantic fiberglass parts that are sort of shingled or nestled together like stacking dolls, like those Russian stacking dolls. And they didn't have carbon fiber that was commercially available when this car was made. But all this whole thing is one big, these gigantic fiberglass, these shells that are put together. These were not that reliable. They had lots of problems with pull out of suspension pieces and shock absorbers and things, because they had these point loading problems. But when you look at this approach, I want you to think of that bike. Okay, this bike came some 60 years. What is that, Steve? What is that? That's 40 plus 60 years later, or 50 years later. And it wasn't until the mid 90s that the bicycle industry was able to kind of hop on board with this idea. We when I was
though? That you make this
Well, it's horrible. It's a death trap.
Yeah.
It's a death trap. It's horrible. They didn't have crash energy protection requirements back then. When I was at Chrysler, I actually worked on this car right here. This is called the China Concept Vehicle. And Chrysler was trying to make a low-cost vehicle for Chinese and Indian markets and East Asian markets that would be inexpensive. And it's a similar approach to the Lotus Elite, okay, in that it's these sort of shells of pieces that are big pieces that are put together to form a monocoque structure. These are actually injection molded. So we got a gigantic molds, and we used an injection molding machine to make these pieces. And it's some type of recyclable plastic. It's a polyolefin, so it can be recycled with little pieces of fiberglass in it. And I think if you weren't expecting much out of your car, it would be fine. But then again, it was a death trap. So we showed this car to Chrysler management. They said, "Oh my God, you can drive this thing, you're going to get killed. Imagine the liability we're going to have." And we said, "Well, it's going to India and China. That maybe they don't have the liability problems there that we have in this country." They said, "Baloney." They said, "Figure out a way to make it crash." And so we found out with this approach, with this injection molded plastic, we couldn't get this thing to meet crash requirements. Okay, and I remember showing my VP the ASHRAE diagram. We've talked about ASHRAE diagrams. Showing him the ASHRAE diagram of plastic. I said, "Tom, it's right here. You're thinking like it's up here, but it's like down here in the lower court. It's not going to work." And I remember he's a big, huge Texan guy, wonderful person. He goes and with a cigar in his hand. He goes, "Oh my God, Tom, you mean we wasted $150 million on this car and it won't work?" He was from Texas. He had this great Texas accent. Wonderful guy. I think he became a country music star after retired from Chrysler. But in order to make this car meet crash, we had to keep adding steel tubes to the inside of it. So one by one, we added steel tubes until we meet crash. But by the time we added all that in, we basically had a welded space frame in there inside the plastic, and the plastic wasn't doing anything. Oops. So this is the Lotus Elise. We talked about this a little bit. This is made out of aluminum extrusions that are joined together with adhesive. You can kind of think of this as analogous to that first Vitis aluminum frame I showed you, where they had the aluminum tubes and they glued them into the cast lugs. Very similar approach here. It's interesting to me. This is kind of new. I haven't seen this before until I was putting this presentation together. Here's a cross section of the tub structure right here. You can see what cross section, what tubes in the cross section were made out of extrusions, and which were just plate material. It's actually fewer than I thought. There's only 1, 2, 3, 4, 5, 6, maybe 7 cross members in the aluminum part, which is kind of surprising. The rear part of the vehicle was made out of a weldment, a steel weldment that was hot dip galvanized. And then interestingly, we talked about the death trap in the fiberglass cars. The front structure in this car is actually made out of fiberglass. It's an aluminum. I'm sorry. It's a fiberglass structure, and it's actually very efficient at absorbing energy. So when you deform metals in a crash, you're absorbing energy by plastic deformation, and you want to plastically deform as much volume of metal as possible in order to absorb the most energy with the least weight. With fiberglass and carbon fiber, when you get to an impact, you have what's called functional sliding. So the fibers slide in the plastic matrix, and that friction absorbs the energy. And that's more how this structure works. Problem is, it's probably only good for one impact. This is the first carbon fiber monocoque in a Formula One car. This is the McLaren MP4-1, and they built this car together with Hercules, which was a carbon fiber company, I think in Utah, in this country. They didn't know what would happen during the first crash of this car in a race, and I think one of its first outings or something, the driver who was driving this had a big crash at the Italian Grand Prix, and they thought he was dead. They thought, "Oh God, this guy's had it." And it turned out that it held up better than any steel structure or aluminum structure they'd ever made previously. They were totally surprised, and the driver walked away. He probably crashed it, well over 150 miles an hour.
They didn't test it before they put the first one.
Not back then, no.
What the heck?
These are race car drivers. They're expensive.
What do you suppose the thickness of the honeycomb is? I probably varies in sections, but
Right. I don't know. I can guess, but I don't know. I imagine it's much thicker than they are today. I would imagine it's much thicker than the wall thickness on this bike. Just because they didn't know they didn't know, no one had ever done this before. They didn't have good simulation tools. they did their best with engineering intuition
Mhm.
and, maybe testing class and things, and they probably put a couple extra layers figuring, okay, it's a fail safe in case things don't work out as planned. This is the kind of further advancement, I think, of this. This is the Porsche Carrera GT from the early 2000s. I mentioned this on our first day. This is an interesting car, I think, because it combines monocoque construction with space frame construction. If you look at the way the area around the engine's done, where they have these sort of discrete structural members that support the engine and the suspension behind it. And again, you can look at this type of structure that's made in one piece. Actually, it's split from here back. So this is one piece and this is one piece. But you can kind of see the similarity between this bike and this car and how they've carried this concept over to that car, or vice versa, depending on. Well, the Kestrel was mid-90s, so there might have been some thought there. Look, they did it on a bicycle. Maybe we could do a similar construction in the back of our $300,000 Porsche here. Some cars that are maybe more common that you see more on a daily basis. I put these up there because they're mixed material solutions. As I tried to impress on you guys, you can't always use carbon fiber for everything because it's too expensive, especially when you're building a car that someone who's not a millionaire is going to have to buy or wants to buy. And so you can get to cost-effective, lightweight solutions by mixing materials. Use material like spice, right? Spice like saffron's expensive. You don't put much of it in your food, but you put enough so it tastes right. The same thing here. Use expensive materials like spice. Where you can use aluminum, you do. Where it makes sense, where you get the big structural benefit out of it. And I've said this before, like maybe it doesn't make sense to use expensive carbon fiber on roof panels because roof panels really aren't stressed that much. So what's the point? The Audi TT is another example. This actually is mostly aluminum. This is what they call a space frame. I don't know if it's really a space frame, but certainly the Audi marketing says it's a space frame.
Can you get the steels based on that Porsche? The weldability, I'm thinking any welding on the
Yeah.
like the weldability between the different flavors of steel. Is that a bigger issue or does that cause a problem?
It does, yeah, because the heat affected zone around the spot weld
Right.
doesn't have the right microstructure
Right.
because it hasn't cooled at some very carefully controlled rates or been heat treated or tempered, right? So you get something around there. I can tell you for sure that the people at Chrysler wouldn't be able to tell you what's there. Maybe the people at Porsche would be deep enough technically to know what's there.
Growing concerns from like the different alloys, because it's a slightly
Right.
similar metal, right? So it's
Right.
galvanic change.
Right, you can't have galvanic issues between aluminum and steel. Typically, they use a lot of adhesive between the two,
Okay.
a lot of plastic, polymer in there to cut off any circuit that would go between the two. We're almost out of time here. The new Corvette's a work of art, beautiful aluminum castings, really interesting, well done. This is the car I think I admire most on the road right now. This is the BMW i3. And this is, this is the first mass volume carbon fiber car there has ever been. I think I told you the story before. When I was at Chrysler, I spoke to the head of body materials engineering about the future of carbon fiber in cars. And I remember he said to me, Don, we'll never use carbon fiber in cars. Even if the material was free, it's far too expensive to make any parts out of it. There you go. Here you go, Rick. There you go. It happened. It happened, and it's a miracle. What besides just the technical hurdle they were able to get over by using carbon fiber, making it safe for crashes and repairable and all these things. What's equally impressive is the fact that they set up a whole supply chain to make the carbon fiber. They work with a company called SGL, which is another German company. And they set up their own carbon fiber pyrolyzation plant in Washington, where they could get cheap hydroelectric power, to lower the environmental cost of the car and the dollar cost of the car. Teslas are neat, but I think this is neater. Okay, don't worry about this. This is a concept I had for trying to get closer to doing what they do on bicycles and cars. Can you make sort of smaller carbon fiber, sort of quasi mid-spectrum, space frame monocoque somewhere in between, in sort of discrete pieces, and then glue them together like they do on these types of bikes? Could you do it in such a way that you have better topology, better transfer of stress from from where it's coming into the body structure to the other end, where it comes in, the points of boundary conditions. You have a more efficient pathway for stress between the boundary conditions. And then finally, Colin Chapman, I just want to introduce you to him. He's not alive anymore. He died a long time ago. Colin Chapman was the founder of Lotus, and he really was the biggest innovator, I think, of the 20th century in lightweighting car structures. And his motto was to simplify and add lightness, and then see if you can use any given component for multiple uses. So he would make space frames, for example, where the tubes also were the radiator hoses. So the coolant would travel through the tubes in the space frame. And they would rust, of course, but he didn't care because if it lasted one race, that was good enough. What he didn't know is that people still drive his cars, and people still drive his racing cars, so there's danger, but he's long dead. Anyway, a lot of people talk about Ferrari. This guy, Lotus, was really the big innovator of the 20th century, both in, I think, a lot of things you have to do with passenger cars and with Grand Prix cars. Okay, so I'm going to stop there, but I just want you to leave here when you're done with this course, and always remember that in order to get true lightweight structures, in order to reach maximum structural efficiency, you can't just focus on the geometry, and you can't just focus on the materials. It's going to take both of those things to get to true lightweighting that minimizes CO2 emissions into the atmosphere, other greenhouse gases, and will reduce the amount of energy we use in accelerating cars or airplanes or bicycles or whatever. So if you guys ever want to talk about anything, if you have any projects, school projects you want to work on, you're working on, you want to know more about any of this stuff, feel free to talk. I'll have my, probably got my email, so feel free to email me anytime. And if I'm also, once or twice a week, I'm in my office over there, 4-142. Thanks, guys. Thanks for listening.
Thanks.